Hello everyone, let's talk about this definite integral here. We have the integrand, that's a floor function of the Ln of x, and then the limits are from 1 to 9, and then we try to find the value for this integral. So first, before we get started, we need to review what the floor function is, and then we want to see how it behaves so that when we plug in the Ln of x into this floor function, what kind of x values that it's going to output, and that will actually help us figure out how to evaluate this integral. So let's get started. First, we are going to review something about the floor function right here, which is that what this function does is that when you input a x value in there, then it's going to output the integer that's less than this one, the greatest integer that's less than this x right here. So for example, if we are plugging in an integer, let's say a 5 in there, then you are going to be getting just a 5. But now if you put in a decimal or a fraction in there, let's say 2.3, then it's going to output the 2 because 2 is the greatest integer that's less than or equal to this number that we are plugging in there. And then if we are putting in a negative value, let's say negative 7.4, then it's going to output the integer that's negative 8, not negative 7, because negative 8 is the integer that's the largest integer that's less than or equal to this negative 7.4. Okay, so that's how it behaves. Now, we are plugging in the Ln of x into this floor function right here. And then we are going to evaluate the integral from 1 to 9. And so let's see what's going on here, because that it's going to be outputting just integer values for us. Now, it feels like the function is not going to be continuous on this interval. Okay, and then you may say, then does that mean that we cannot apply the FTC part 2 to evaluate this integral? Well, if we have finitely many jump discontinuities, then we can still evaluate this integral. So let's check what's going on here. Okay, so now to start, we are going to start with the lower limit right here. Okay, so the lower limit, it's going to be what? If we plug in the 1 into the Ln function, right? I'm not considering the floor function yet. I'm just looking at the Ln function. Ln of 1 is going to be 0, okay? And then now, what about Ln of e? Ln of e is actually equal to 1. And so because we know that the Ln function is continuous, and that means we are going to have, and it's also an increasing function, strictly increasing function. So what happens is that for all the values between 1 and e that we plug into the x, we are going to get the output for the Ln function to be between 0 and 1. Okay, so from here, and actually I should mention that e is about what, 2.718, right? Okay, that's just the approximation. That's all we need right here. Okay, and now let's think about what's going on here. So we know that from those two, and what I just mentioned, right? Ln is a continuous function and it's also a strictly increasing function. So what happened is that for all the x values that we plug in between 1 and e, then the y values would be between 0 and 1. So what we can say is that this would tell us that the Ln of x would be between 0 and 1, right? For all the x values that are between 1 and e. Okay, so that's what happens right here. Now, do you see what's going on here? I think I should highlight this result right here, which can be helpful. Okay. Okay, so for all those values between 1 and e, then when we plug them into the function, then this function will be between 0 and 1. Okay, now let's continue. Let's look at the next one. The next one is when we have e squared. Why? And then you may say, why do we pick e squared? Because that's actually outputting a 2, right? When you plug that into the the ln function. And so what is e squared equal to? That's approximately, if you're just squaring the 2.718, then you can get an approximation. That's actually about 7.389. Okay. And then actually, if you just, and you know that this value right here is actually still less than the 9. So we should just go one more, right? We should just go one more. We have ln of e to the third power, which is actually 3. And then you know that for e to the third power, that's actually cubing the e, which is cubing this number right here. And then you are going to get something that's close to 20.086. And now that's, as you can see here, that's beyond this 9, right? That's far beyond this 9. So we are going to cut off the intervals from starting from 1 and then to somewhere between e squared and e cubed. What is that somewhere? That's really just 9, right? We just cut that off there. Okay. Now, let's just look at those two right here. The ln of e equals 1, and then the ln of e squared is equal to 2. And so you know that for the lower bound, which is 2.718, and then the upper bound is the e squared, which is 7.389. Between those two x values that we plug into the ln function, the y values would be between what? Will be between 1 and 2. And so now we can draw another conclusion right here, which is, so we can say that the ln function, right, would be between 1 and 2. For the x values, right, for the x values between e and e squared. Oops. So we have e and then e squared. Okay, so the number will look like what? When you plug in any numbers between e and e squared into the ln function, the output will be between 1 and 2, so it looks like 1 point something. Okay, and then now we just compare those two, and then from this one, what happens is that so we're not going to go all the way to EQ because that's too large for our limit, right? For our upper limit, we are just going to stop at 9. But the lower bound in this case would still be 2 for this function. And so if you start plugging in values, okay, between e squared, and then instead of going all the way to e cubed, we are actually just going to cut it at 9, right? So because you know that e squared is equal to 7.389. So this is 7.389, and then between 7.389 and 9. And then what happens? Then our output for the ln function will be between what, 2 and what? If you plug in the 9 to the ln function, then that would just be ln of 9. I think I need more space, so let me just redraw that. So it will be 2 less than or equal to ln of 9. Okay, so those are all the 3 intervals that we have. And now what we can do, I think I need more space. So let me just move those. Let me just move those down here. And then because I really need more space, so I need to organize my work a little bit. Okay, so now that's good. And then let's actually just graph this function here and see what's going on. Okay, so let's do that. And then you may say, why do we need to graph the function? Can we just integrate? Remember that I said that there will be jump discontinuities, right? The function is not continuous from 1 to 9. So we want to see what the function looks like. And then we can do the integration. Okay, so let's just graph it. And since we are actually just dealing with positive x values right here, we do not really need the second quadrant and the third quadrant, right? So we are just going to focus on the positive x side right here. Okay, so we have our x-axis and the y-axis, right? We have the x and the y right here. And then as you can see here, for the y values of the function, you are not going to go too far with the y values, right? So we are going to, actually, we don't even really have any negative x values. So I'm just going to move this x-axis down a little bit more so that it's easier for me to draw. Okay, so right now we are going to just label that scale as 1, right? And then there was a 2 here, and then there was a 3 here, and then I think that's it, right? We probably don't even reach 3 because that's too far already with the x value. We only go up to 9 for the x value. Now, for the x value for the 1, then we are just going to start with the 1 right here. So this is 1, and then we can actually just label those e square, and so on, right? E square is what, 2.718, so we can just label that as right here. So this is e. No, actually not e square, right? That's just e. And then the e square is what, 7.389, right? So e square will be right here. And then there was also the 9, right? The 9 is actually close to the 7. This is not drawn exactly, right? This is really just rough sketch. Okay, so just to help us, I should just label the numbers right here. So 2.718, right? And then the e square is just going to be 7.389. Okay, so now let's see what's going on. We also need to know how the floor function behaves, right? So pay attention to that. That's just something to keep in mind right here. Okay, so for the values, right, for the x values between 1 and e, which is for all those values between 1 and e right here, our function is actually going to be outputting a value that looks like 0 point something, because it's going to be between 0 and 1. And now let's think about this. If you have if you plug in 0 into the function, right? No, actually, I mean, if you replace the ln of x by 0, then you are actually just plugging in 0 into the floor function. Okay, so in this case, so let's do some more work right here. You plug in the 0, then you're just going to get 0. And then now, what about if you plug in any of those numbers between 0 and 1? Like if you plug in things like 0.5 or 0.7, and then what are we going to get? We are going to get 0. And all of those numbers are 0, right? As you can see here. Yeah, as long as that number is between 0 and 1. What about if you plug in the 1 into the floor function? It's going to be what? It's going to be 1, right? No, actually, so if you plug in that, it's going to be 1. Now, what about something that's really close to 1? You are still going to get 0. So do you see what's going on here? We are actually getting a constant function. And so from 1 to e, all the values, right, that we are getting would be 0, except that when you plug in the 1 in there, you are going to get the 1. So when you plug in the e into the x, which will output a value of 1 in here, and then when you put that into the floor function, then you are just going to get the 1 here. So now how do we graph this? How do we graph this one right here? It's just a horizontal line, right? Including the 1 right here, but not including not including the e. So I'm going to put an open circle right here. Okay. Now that's how we graph the first one. And then now you may say, what about the second one, right? The second one, let's look at the second one here. Okay, so for all the values between e and e squared, for all the x values, so we are actually looking at this interval right here, e to e squared. And how do we graph this one? If you look at this, we know that it's going to output an L1 of x value that's between 1 and 2, right? So now let's check a few of those values right here and see how it behaves. If you plug in the 1, then of course we just check that it's equal to 1. You plug in things like 1.2, then it's also going to output a 1 in here. Something that's really close to 2, right? You can get as close as you want, you are going to get, well, no, not 2. You're still going to get 1. But by the time that you plug in the 2, then you're going to get the 2 here. Is that okay? So 2 is not going to be included. So that means when you plug in the e square, which will output a 2, that's going to output the 2 for you. But then for anything that's really close, okay, for anything that's really close to 2, but less than 2, then you are still going to get 1 as the output for the floor function. Okay, so as you can see here, you are still going to get a constant function here on this interval from e to e square, and then it will be a horizontal line. And so now, because the 1 is being included, right, when you plug in the e, you are going to get 1. So we are going to get a solid dot right here, and then we are going to get a horizontal line segment from e to e square. And then now we put an open circle here. Okay. And then now, just following the same idea here, you know what's going to be for the last interval here from e squared to 9. So all those ln values that you are getting, right, would be between 2 to ln of 9. And ln of 9 is actually still less than 3, as you can see here, because only when you plug in 20.086, the e cube, then you are going to get the 3. So this is still less than 3, right? So for all those values that you're getting here, what are we getting here? We are getting the 2, and I'm not going to show it right here anymore, right? So we are going to be getting starting point at the e square, right? Starting at the e square, and then the 2, right, at the 2, and then at 9. And actually this would also be a solid dot here. And then so we graph this function on this interval, right, from 1 to 9. So it's a piecewise function right here. And actually I don't need this anymore, so I'm just going to erase all that. Okay, now the question is, how do we evaluate this integral, right? It comes back to evaluating the integral. And as you can see here, there are 2 jump discontinuities on this interval for this function. And so we are going to break this integral into 3 integrals right here and then calculate each one. Okay, so let's do that. And so we are going to be getting, right, starting from 1 to 9, and then dx. It's going to be breaking, going to be broken into, now let me just use the same color for those integrals right here. It's going to be the integral from 1 to e. Okay, that's our first interval here. And then actually the integrand stays the same, right? And then plus, now the second one is going to be from e to e square. Adding, now the blue one is from e squared to 9. Okay, so now we get 3 integrals here. And then let's just calculate each one. How do we calculate each one? It's actually quite easy here, because all those 3 line segments above the x-axis. So when we calculate the definite integral, it's really just finding the area under the curve. And so there is no area for this one, because you know that that's just all 0 right here, right? And so if you just look at the graph, you can actually find the area without actually doing any real integration, right? So the answer for the first one would be 0, okay? And then now what about the second one right here? Let's look at the area under the curve. So we are looking at this region right here. Okay, so we are looking at this region. We are finding this area right here. How do we find this area? So you know that it's really just a rectangle, so we can do length times the width. The length is actually e squared minus e, right? We find the distance, so e squared minus e. And then what about the width? The width is just 1, right? So you get the 1 right here. And then now continue with the third one. The third one is going to be from e squared to 9. And then you are still going to be getting a rectangle. So you look at that one. You see what's going on here? We are having, what is that? That's the length is 9 minus e squared, right? So we have 9 minus e squared. And then what is the width? The width or the height is actually going from the x-axis all the way to 2, right? So the height is going to be 2. And then now we can continue with the calculation. So what is the answer here? E squared minus e, right? That's e squared minus e here. And then plus, okay? So now distributed 2. So we are going to be getting 18 minus 2e squared. So let me see. We have e squared minus 2e squared. We get negative e squared minus e, and then plus 18. And sometimes we just put the positive number in the front, right? So just to make it look better, minus e, and then minus e squared. And then we're finished with the problem. So the value for this integral will be here. And you can actually still do integration if you do not really want to interpret the integrals geometrically. How do we do that? Let's just think about this. There are actually just 3 constant functions for the integrand. So do you see what's going on here? This is 0. This integrand is 0. What about that integrand? It's just always going to be 1 on this interval. So you just put the 1 right here. And then for that one, it's going to be 2. And then you just integrate using the fundamental theorem of calculus part 2, and then you are still going to get the same answer. Okay, so how do you like this problem? It's actually quite fun, right? We have a function that has a few jump discontinuities, and then we can actually still figure out the value for the definite integral. Okay, so that's it. If you like this video, please subscribe to my channel and then leave me a comment, give me a like, and then please check out my other videos as well. Thank you for watching this one. I will see you next time.